Okay, so welcome to the class. So last time we had looked at the connection between relative entropy and other entropic quantities. So relative entropy. And now, so let me recall the definition. So the relative entropy of two quantum states in the same Hilbert space A was defined as trace. So if food poisoning is gone, Shannon?
It's better. It's better. I mean, I'm a little weak, but it's much better than what it was that day.
I see. So no need of antibiotics.
No. Just doi bhat is working.
So okay, fine. So this is this was relative entropy, and now we had defined the various entropic quantities, in particular mutual information. So mutual information between A, B under the joint state rho. So of course, for this to make sense, I have this underlying joint state rho A, B. In general, it's a mixed state. So we have defined it the usual way in terms of the Shannon entropies. But at the end of the last lecture, we saw how this is equal to this relative entropy, exactly as in classical. And this already had nice implications. So this implies that relative entropy is always non-negative. So that was because we had proved even before that the relative entropy of any two states, rho and sigma, is greater than or equal to 0, and it is 0 if and only if rho is equal to sigma. Okay, so let's recall that. So this is always greater than or equal to 0. Equal to 0 if and only if. So far so good. And already it proves this non-trivial result that the mutual information is always positive for any joint density matrix. So this further implies what I'll call the sub-additivity of the Shannon entropy. It's called sub-additivity. In fact, equivalent, the sub-additive entropy is equal to saying that the mutual information is always non-negative. Okay, and this also tells us more, right? Because this tells us, so this tells us more. So it also tells us when the mutual information is exactly equal to 0. That happens when this relative entropy is exactly equal to 0. Okay, and that only happens if rho AB is equal to the tensor product of margins. So let's write that down. So I AB equal to 0 if and only if rho AB is actually a tensor product state. So all this we got by connecting mutual information to relative entropy. So this is just the quantum analog of what we have done in the classical part of the course. But now, today we'll look at some new stuff. I mean, things which are easy to prove classically, but they're highly non-trivial quantumly. So I had just mentioned it in passing at the very end of last lecture, but now I'll write things down formally. So the question is, before I come to the question, let me write down explicitly one more implication of the non-negativity of mutual information. So IAB. So another equivalent way of saying it is that H of A given B under rho. So the conditional entropy is always less than the unconditional entropy. Or in other words, conditioning can only decrease entropy, which is equal to the other one also. And here, I mean, we take the definition of conditional entropy is H. So again, this is nothing but mutual information is greater than or equal to 0. And just to refresh your memory again from the last lecture, it's fine we define conditional entropy this way, okay? And we have already seen that conditional entropy can in fact be negative, okay? And how negative? We also know that this is always greater than minus HA. So this is the Archimedean, which we haven't proved as yet, but today we are going to prove it. So conditional entropy can indeed be negative. Conditioning always reduces entropy. So far it's akin to classical, but conditional entropy can be negative. This is completely different from classical. And we have seen the example of the EPR and see how low it goes. So we have examples which saturates the lower bound out. It can indeed go this low. Okay. And yeah, to refresh your memory, if I define conditional entropy this way, I can also connect conditional entropy to a relative entropy exactly as classical. So this is log A minus the entropy of the joint state with respect to this the completely mixed state of the uniform probability distribution over A, which is just this tensor, the marginal node. So this is all that we have learned so far. Any doubts, queries? Okay, no. So let's go ahead.
I have a
No, let me add the question.
sorry.
So the question is, okay, so I know conditioning
Hello.
reduces the entropy, but what does further conditioning do? So yeah, I had written this question also. Is H of A given BC less than H of A given B? This is for all. Take any, now it's a tripartite density matrix. So classically, we know this is true. Further conditioning only reduces the entropy. But the question is this true quantumly? And now if you open things out and say, oh, I mean, this must be true because didn't we just show that if there is no C out here, or in other words, if C is one-dimensional, okay, we just check that this is true. This came from subjectivity of entropy, which is nothing but non-negativity of mutual information. But now if you open this out, you'll see that it does not reduce to non-negative to mutual information. It reduces to a different relation. So let's open this out. So this is equivalent to the following thing. So you can open it out and then see that this two are equivalent. Simple exercise, verified at home. Okay. So this is not looking like subadditivity of entropy. Okay, it is also not looking like mutual information, but I mean, from our classical experience, we know this is equivalent to the following thing. That so classically, I mean, we know how to define this, right? This conditional mutual information. So one way to think about it is that I fix B to a sample point, okay, in its sample space. I fix B to some little b, and then I'll get the conditioned joint distribution on the system AC, conditioned on little b. And then I compute the mutual information and I average this over all the little b's. Okay, so little b's are chosen according to the marginal b. So there was this classical picture that the conditional mutual information is actually an average of some mutual information quantities. Okay, an average of some unconditional mutual information quantities. Now the unconditional mutual information is greater than or equal to 0. We know that. So its average is also greater than or equal to 0. So this would have been a classical proof. Okay. But unfortunately, in the quantum world, we have no analog of conditioning on b equal to little b. This is the whole problem. So that is why in the quantum world, we cannot just simply claim that this is true. Okay, so we cannot simply claim that this is true. I mean, the conditional proof will not work. So is this still true? Not clear. I mean, if you open it out, so I'll say that, okay, I will not do conditioning. I will instead write the conditional mutual information in terms of good old entropies, no conditioning anywhere. But when you open things out, you get exactly this relation, the strong subadditivity. So yeah, so let's give the name. So this one is called the strong subadditivity.
This requires the full power of Araki-Liev, right?
No, Araki-Liev was a triangle inequality.
Oh.
Okay, so this is something else, a strong subadditivity of the Shannon entropy.
So I mean, I've always been a little confused about this. So subadditivity is HAB less than equal to HA plus HB.
Correct.
That is just subadditivity.
Yeah.
Strong subadditivity, what it does is it essentially adds this B system and says that
well, the way I wrote it out here, take the subadditivity of A and C and then put in another system B. So B is the conditioning system. So if you look at this, look at the form of that.
Right.
Yeah.
Okay.
So B is common. B is the conditioning system. B is common on the left. Okay. And on the right, B stands out here.
Right. Okay.
So, of course, you can write down the analogous thing with conditioning system C and all. I mean, all it will boil down to is if I write with conditioning system C, then it's the mutual information of A with respect to B conditioned on C.
Yeah.
So classically, nobody bothered to single out this strong subadditivity simply because, I mean, okay, I mean, this inequality, we know it's equivalent to this conditional mutual information being positive, and we know that is positive simply because I will fix B to little b and repeat the old argument. Okay. But quantumly, we cannot do that. So that's when people single it out and realize that this is a non-trivial thing to think about, the strong subadditivity. And it's related to things we take for granted, that further conditioning reduces entropy, conditional mutual information is positive, so on. Okay. But I mean, all these are equivalent, fine, but we need a proof of that. And right now, we don't have a proof in quantum. Further questions? Is this clear to you, Hari?
I just have a question about something that you wrote earlier. I think my audio was broken, so I couldn't ask. Can you just slide up just a bit? Yeah. So this H A given B this relation, this is log dimension minus the relative entropy. So this is also equal to relative entropy between rho AB parallel just identity on A and rho on B, right?
Then you have to remove the log area.
Yes, that's exactly the
yeah. But I mean, I'm not writing that because right now I'm only
define relative entropy for states.
Yeah, relative entropy for states. So I mean, they have to be trace one or whatever. Relative entropy for probability distribution. So they're total mass has to be 1. But
Right.
you can define relative entropy for any two positive vectors. Okay. So in other words, for any two positive similarity matrices, same definition.
You're right. So why I asked was that usually you, like the min and all those things in quantum, we define them. One way to define them is like minus d max epsilon of rho AB parallel identity.
Yeah, it's all the same. Everywhere there you can put a log A here and come to this.
Okay. But
I guess want to shorten their equations, so they, ignore that log A, but the price you pay is if you write identity. You cannot write identity divided by A.
Okay.
So it's no longer trace 1. But it's basically, this is trace 1 by, it becomes trace A if you just write the pure identity out here. Okay, so that removes the log A out here, but that's fine. Okay, but the problem is if you do it, then you have to settle for the fact that this D is now negative. It has become negative simply because the identity here is huge trace.
Right.
Okay, so so I don't like that approach, because you will suddenly see that D is become negative and then you wonder, oh my God, what's happening? Okay, so that happened because this trace was larger than 1 out here. Whereas earlier we were saying that D is positive, okay. But D is positive only when both
those two are states
have trace 1.
Right.
Yeah. So any questions? Hari, is this clear to you? So,
yeah, this is fine.
Okay. So now the strong subjective question we'll connect to our main hammer that we have in the arsenal. So that is the data processing inequality for relative entropy. So remember classically how we stated the data processing inequality. So the simplest way of stating it, so I'm writing the quantum analog of the class. So take two density matrices in the space A tensor B. Now if I trace out the system B, so in other words, I'm only looking at the margin on A, that will reduce the relative entropy. So this is the statement that I write. Now, already we saw classically that this implies that take two states rho and sigma, okay, take two propagation rho and sigma, same sample space, apply a private coin algorithm. Okay, so you get start with P and Q, applied my algorithm A, so I get AP and AQ, and that only reduces their distinguishability, that only reduces the relative entropy. So now if you're applying a private kernel algorithm, that's more akin to the informal meaning of data processing. Okay. So I said that that's what one may have been used to, but then we saw how every private kernel algorithm can be obtained by attaching an ancilla. So classically, the ancilla had some zero workspace and it had the private coin as another register. Then I had applied a reversible algorithm, so which is a permutation of bit strings. Okay, and finally, I had discarded the ancilla register. And we had argued there is only the third step, the discarding step, which is reducing the relative entropy. So quantumly also we saw what was the general quantum operation, okay, which are obtained by you attach an ancilla initialized to 0. So we saw that in the quantum world, I don't have to say that the ancilla has two parts, like the all zero workspace and the private coin, okay, because the private coin can be simulated in the next step of the procedure. So in the quantum world, the most general thing would be you attach an all zero ancilla there, then do a unitary operation on the larger system. Okay. So which is the analog of the reversible classical operation. So do unitary operation on the larger system and then you trace out the ancilla. And now, as you can believe, if you attach an ancilla, okay, that's not going to change the relative entropy. If you do unitary transformation, also that's not going to change the relative entropy. Just maybe I'll for your eyes, I will show you what was the definition of the relative entropy out here. All the way up, right? So you can see that if I attach an ancilla, nothing changes. The whole thing moves out in ancilla, the trace does not change. If I apply a unitary on rho, so rho becomes u rho u inverse, sigma becomes u sigma u inverse, but you see that the trace remains the same. So the first two steps again don't change the relative entropy. It's only the third step that reduces the relative entropy. Okay, the step of discarding or tracing out. And that's exactly what I wrote. So this is the crucial step. If you forget a register, you reduce the relative entropy. So let us like assume this for now. So I've not yet proved it. So let me emphasize that I've not proved it. So assume this. And let us look at its consequences. So
when now using the log definition, it's clear, right? What to do?
So let us look at one of its consequences. So okay, so the consequence that I'm looking at, so let me go to the next page. It's best. Yeah. So here is something. So again, this is something which is quite familiar from our classical intuition. So that is this. That says that, which is called monotonicity of mutual information. So sometimes the data processing inequality for relative entropy, the way I have written, okay, the way I have written this data processing inequality, when I'm talking of tracing out the system B, often this is also called monotonicity of relative entropy. So let me write it also called monotonicity. So it's monotone in the registers. Reduce the registers, relative entropy reduces. So I have monotonicity of mutual information. This is again, which is familiar to us. So what is that? So let's say I take the information between A on one side and BC on the other side. This is greater than the mutual information between A and B. So again, I mean, it is something which feels almost obvious classically, but yeah, classically it's easy to prove this. So informally it says that the mutual information between A on one side and BC on the other side can only go down if the other side forgets C. So let us see what this is equivalent to. So if I open out the mutual information in terms of all the Shannon entropies, so what this becomes equivalent to is H of AB in check plus H of BC. Let's see, this is correct. It's greater than H of BC plus H of C. Is this the correct form? So H of A plus H of BC. It must be H of A. Greater than H of, no, H of A is common. So H of A minus H of A BC.
No, there's a H of B missing.
No, so and that is H of A plus H of B minus H of A. So this
No,
is
that's H of B. That's H of B. So it's plus H of B.
Yeah.
HABC plus H of B.
That is H of B. Yeah, so that's just appropriate. So this is equivalent to this. Okay. So this is, as you can see, the monotonicity of mutual information is nothing but the strong subalternativity. Okay. So everything that we have discussed a few minutes ago, right, which was related to strong subalternativity. So strong subalternativity is same as saying conditional mutual information is positive, which is saying that further conditioning only reduces the entropy. Okay. It turns out it has another equivalent form, which is monotonicity of mutual information. And now, but monotonicity of mutual information is nothing but an application of data processing inequality for relative entropy. So let's write down. So the left hand side mutual information is this relative entropy. And the right hand side is this relative entropy. So all I've done is I have discarded the system C out here. I've discarded the system C and okay, so now at least we realize that all this strong subjectivity and everything around it, everything follows once we prove our hammer, which is the data processing inequality for the relative entropy. So this is again analogous to the classical treatment that we did in the first half of the course. Okay. So really, I mean, there's only one thing left to prove, which is the data processing for relative entropy. So that will not prove today in this lecture. That will prove by the end of the course. But that historically has been a very hard and deep problem to do. Okay. And it was proved by various people using sophisticated matrix analysis. Okay. So Lieb was one of them, and then there are other people, Ruskai and others. So till recently, I mean, the only proofs used some heavy mathematics. But in this course, we will actually prove it elementarily using the power of our one-shot techniques. Okay, but that will require several lectures. By the end of the course, hopefully, you'll see.
I have a question.
Hmm.
So suppose you prove it for D max epsilon, or yeah, D max epsilon. And then you say that you use this QAEP thing to say that in the limit. So there's this one argument that I'm always struggling with. So just because for every n the inequality holds, is it also, I mean, you need some sort of uniform convergence sort of thing to say that even the limits.
You prove it for n, divide by n and take the limit. So you just use asymptotic equipartition.
No. Yeah. There's a like analytic issue there, right? You need to say you're saying that for every n, fn greater than equal to gn, but something like this. But to say this is true for the limit also, you need some sort of uniform convergence.
I mean, all you need is no uniform. You just need limits. You have two sequences.
Oh, right. You have to
an greater than or equal to bn, and now I take limit an, limit bn. Okay.
Yeah. So
as long as both the limits exist, you can say a is greater than or equal to b.
Right. You don't need uniform. Okay. Yeah.
All that is simple. The hard part is to, I mean, evaluate that limit. I mean, that is the asymptotic equipartition, the quantum asymptotic equipartition. So we'll do that. Okay. Again, there are elementary ways of doing it now. Earlier things were not elementary. But anyway, right now we'll see how the Araki-Liev inequality follows from strong subadditivity basically. So ultimately it also boils down to data processing for relative entropy. Okay, so remember what is the Araki-Liev inequality? I want to say that the so classically, of course, the entropy of AB was greater than or equal to entropy of A, but quantumly we know that's not true. But we have this, and then there's the other one also, which is H. So you can combine it and write a mod, but I prefer to write it separately. Okay. So let's prove this. So what we do is, so of course, I mean, when I'm doing this, there's this underlying joint density matrix rho A sitting in the picture to make sense. So let me take a purification of rho A. So I will tell you more what this means. So let me write down here. So what's the purification? So of something. So I have a density matrix, a general quantum state out here. Now I'll construct a quantum state on a larger system. So there is the original system, which is AB, and then I put in another register. I'm calling it C here. So C is sometimes called the purifying register. Then I'll cook up a quantum state in ABC. That quantum state will happen to be pure. That means that quantum state is a rank 1 density matrix, okay, which for simplicity I will describe by the vector, the eigenvector with eigenvalue 1. So that is what I've written by ket rho ABC. So really the density matrix on ABC is the ket bra rho on ABC. Now, so rho ABC is a pure state, and if I trace out C, I will get the original density matrix rho A. Okay, so this is what is called a purification. So a purification is obtained by attaching one more register, hunting for a pure state in the larger system, okay, such that when I go back to the old system, take the marginals, I'll go back to the old state. So all this means is that trace out C of ket bra rho on ABC is equal to rho. This is what purification is. And remember, we have done the Schmitt decomposition, the nice way of writing down any entangled state. So from the Schmitt decomposition, I can even describe a canonical purification of rho AB. So let us say the density matrix rho AB. Remember the density matrix, if I write it as eigenbasis, I can say that it's a probability distribution over its eigenstates, over its eigenvectors, right? Because the eigenvalues are positive and add up to 1. Any density matrix or any general quantum state is a probability distribution over its eigenvectors. So it's a probability distribution over certain pure states. So that's what I'm writing. So let us say it's lambda I, and remember these eigenvectors are in the system AB. Okay? And in general, they're entangled vectors, but that does not matter for us. So rho AB is like this, and what do I know? I know that lambda I is greater than 0, and summation over I lambda I. So this one. And now I will write down a particular purification. So this I define to be sum over I square root lambda I, then pi. So this is on the system AB. And let us say wi on the system C. So to write that, all I need is, I need a bunch of orthonormal vectors ket wi on the system C. Is an orthonormal set now you may say that how do I know if there's such an orthonormal set? So fine, take the vector space C. So take the vector space C to be of dimension, at least the dimension of AB. So how many orthogonal eigenvectors vi could there be in AB? At most the dimension of AB. So fine, C is large enough dimension. Choose an arbitrary orthonormal set in C, and then set up this matching anyhow you want. So with V1 I'll couple W1, V2 I'll couple W, and just write this down. So this is a pure state. Okay. You can check that it's length 1. So this is a pure state. And again, from what we have seen earlier of the Schmitt decomposition, it's easy to see that take this pure state, write it as ket bra. Take this pure state, write it as ket bra, and trace out C. I'm going to get back the good old. Check. Okay, so is this clear? how to construct a purification. So purification always exists. All you need is then new purifying register C should be of large enough dimension.
The constant which is like multiplying, it's lambda I, like why is it root lambda I, like when we run the purification?
It has to be length 1, no? So look at that. So these are all, I mean, like as I run over I, these are orthogonal vectors. Okay, so if I take the length square of this, it will become summation lambda.
Oh, okay. Yeah.
And when you form a ket bra, so I mean, that's reason 1. Reason 2 is when you form a ket bra, okay, so I'll get cross terms for I prime. Okay, and it will turn out that the cross terms where I is not equal to I prime will vanish when I take the partial trace, when I discard the C. And but for I equal to I prime, then the cross terms will have a lambda I. So maybe I should do it. It's 2. Because the notation is still sort of new. So this is sum over I prime. So lambda I prime. Right? And now I have I W I C, and here I have I prime. So so this is just product of matrices. Right? So and then just usual properties of tensor product. I prime tensor. And now if I do the partial trace, trace out the register C, so this will be so I'll just, so on the system C, I'll just take the trace of this, the Borel trace. So W I prime C. But then, I mean, this is a rank 1 system, so you can easily write down what the trace is. So that will be lambda I prime. This is W I prime bra ket W I. So again, I mean, one way to see it, I mean, this was a ket vector, this was a column vector, this was a row vector. So this is matrix multiplication, multiplying a column vector by a row vector. Cyclic property of trace, I can take the row vector on the left, okay, and then it is a row vector multiplying column vector, which is nothing but this inner product. And now I use the fact that the W is orthogonal, so the summation becomes only over. Summation becomes only over I. So this is lambda I. So for I equal to I prime, I mean it's the same vector, so it's length 1. That's it. I not equal to I prime, that is 0. So is this calculation clear to you?
Yeah.
So this is indeed a monopoid purification of rho A. Good. So let's start with this one. So we call whatever I call ABC. Purification. So now, What do I have? Yeah. So now if I apply strong subadditivity, what do I have? I have h of which one do I want? C out here. Yeah. So let's see. So I'll write the strong subunity in this form. H of so this is larger than, so take A to be the common system, H of A, B, C plus H of A. Okay. So this is strong subadditivity. But let us look at that. So remember, rho ABC is pure. So this thing is equal to H of B. And right, so, and this is again something that we've seen before, that so if I take rho ABC, let me write it as rho ACB, there is this Schmitt decomposition. So let me use another index. So there is some square root mu j, and then there is some Vj on the system AC, and there is this Wj on the system B. This is a Schmitt thing. So the Vj's are an orthonormal set, the Wj's are an orthonormal set in the respective spaces, and there is this bijection from Vj to Wj. Okay. And then there is the Schmitt coefficient square root mu j. But then we had interpreted what these coefficients are. So they are the eigenvalues of the respective density matrices. So from the Schmitt guy, so for example, this implies that the reduced density matrix rho AC was summation j mu j and Vj, right? And similarly rho B. Okay. So it has, of course, different eigen vectors. So in one case it was Vj, the other case it was Wj, but the eigenvalues were the same. So we have this, right? So because the eigenvalues are the same, that entropy of AC is the same as entropy of B. Is this clear? Yeah. And this is a pure state, so its entropy is 0. So we are done. So this means, so what I've shown is that H of AB is greater than. So is this clear now? Yeah. Hari, clear?
Yeah.
Yeah. Okay, so we have proved strong subadditivity. I mean, we have proved that Araki-Liev is also a consequence of strong subadditivity. So now you see how important is strong subadditivity, or how important is data processing inequality for relative entropy. Okay, so with all this down here, so let us proceed. Okay, so now we have defined entropic, the Shannon entropic quantities for the quantum states. Okay. Now I would like to define the one-shot entropy quantities for the quantum states, exactly as analogous to what we did classically. So it's I think nice to start off with a page for that. Here we page in our study. So one short quantum entropy. Okay. So we will start off with the one-shot quantum hypothesis testing relative entropy. So let's call it the hypothesis testing relative entropy. It's always smooth. Let me add the smooth one shot. That's what we want. So classically, I mean, we had done quite a bit of study. Like, I mean, we had defined the entire Renyi family, D alpha, okay, and the smooth Renyi entropies. But then we said that all the Renyi entropies basically boil down to 3 of them. The D alpha for alpha less than 1 boils down to D0, which is, I mean, strongly related to the smooth hypothesis testing relative entropy. Okay, so the smooth D alpha essentially boils into smooth D0. We had a definition of D0 out there. You can, I mean, come up with analogous definitions quantumly, but the moral of the story was the smooth D0 is very closely related to the smooth hypothesis testing relative entropy. So that's one end. At the other end, when I took D alpha or smooth D alpha, where alpha is larger than 1, that boiled down to D epsilon infinity or D epsilon max, as we called it there. Okay. So, and then in the middle, when alpha is equal to 1, okay, then we never talk of the smooth version of that. So when alpha is equal to 1, that was the Shannon relative entropy. So we have defined the Shannon relative entropy quantumly already. So we just have to define the other 2 ends. Okay. So to define what is the smooth hypothesis testing relative entropy at the like alpha equal to 0 end, and we have to define the smooth max relative entropy at the alpha equal to infinity end. So let's start off with the alpha equal to 0 end. Okay, so this is so just summarize this kind of figure. So this is almost the same as D epsilon zero, whatever that quantity is. So anyway, so here's the definition. So D epsilon H, the smooth hypothesis relative entropy, is the exact quantum analog of the classical definition. So I have rho and sigma in the same Hilbert space H. So this is defined as log subject to so let's understand what this definition is and understand why it is the exact quantum analog of this. So yeah, there's a negative log, blah blah. Let's not bother about negative log. So what is the quantity that we are optimizing? So we're minimizing this quantity trace of pi sigma. So what is pi? Pi is a positive semi-definite matrix. That's what the notation means out here. The notation 0 less than or equal to pi. So 0 is the all zeros matrix. Okay. and it's all zeros matrix in the system A. And then less than or equal to just, so in this notation of matrices, like if I have two Hermitian operators, and like I'll say that M is less than or equal to N, I mean, is defined to be the operator N minus M. So M is Hermitian, N is Hermitian, so N minus M is of course Hermitian. But M is less than or equal to N is saying that N minus M is positive definite, positive semi-definite. So that's what this means. Okay. And this is the partial order on Hermitian operators. So here, this is just compact notation to say that 0 less than or equal to pi is just compact notation to say that pi is a positive semi-definite matrix. Pi less than or equal to identity. So I know what this means. This means that identity minus pi is also positive semi-definite. So what does this mean? This means, see, pi is a positive semi-definite matrix, so its eigenvalues are all greater than or equal to 0. And saying that pi is less than or equal to identity means all the eigenvalues are less than or equal to 1. So now recall the classical definition. Classically, this was a private coin algorithm or a hypothesis test. So what was a hypothesis test? A hypothesis test on the sample space A was an assignment of acceptance probabilities for every sample point A. So if I think of pi as a diagonal matrix, okay, so I mean, remember classical probability is embedded into the diagonal in quantum. So if I think of pi as a diagonal matrix, okay, so pi is a diagonal matrix with diagonal entries which are between 0 and 1. So in particular, I mean, this operator inequality means that if I go to the eigenbasis of pi, so pi is of course diagonal in the eigenbasis, and its eigenvalues are between 0 and 1. So another way of saying it is that like pi is a Hermitian operator whose eigenvalues all lie between 0 and 1. That's what it is. So this is nothing but my classical hypothesis test. Okay. So the test assigns the acceptance probabilities, which are numbers between 0 and 1 for every sample point let A. Now this test pi should accept rho with probability at least 1 minus epsilon. I'm only going to consider those tests in my optimization which accept rho. So rho is like the positive hypothesis that is to be accepted with probability 1 minus epsilon. And remember, we have seen our measurements, right? I mean, so this pi is a measurement operator, okay? And the probability of this measurement operator succeeding on a quantum state is given by this expression, trace of pi. So this is again familiar from the classical. Classically, everything is diagonal, right? So pi is a diagonal matrix, rho is a diagonal matrix. It's just a probability distribution. Trace of pi rho is nothing but the probability of accepting the positive hypothesis, right? So for each sample point A, I have an acceptance probability, and that sample point A will come up under the probability distribution P with some probability P. So the classical analog of it, let me write down, would have been summation over A. So pi A comma A and rho A comma A, diagonal. So this would have been the classical analog of this. And this just says that the positive hypothesis is accepted by my test with probability at least 1 minus epsilon. So I want those tests which accept the positive hypothesis with probability 1 minus epsilon, but accept the negative hypothesis with as low probability as possible. So this is what I'm trying to minimize. Minimize trace pi sigma. And then you take a negative log. Call it. So this is the exact quantum analog of the same optimization problem. And classically, the optimization problem was this, and this was the constraint, right? This is greater than 1 minus epsilon. And so the constraint was a linear constraint. And so what was the unknown? The unknowns are the pi's, right? So these are the unknowns. Okay. And the unknowns are between 0 and 1, right? So 0 less than pi, less than or equal to 1 for all A. So I had that. So I had linear constraints classically. Okay, so these are the linear constraints, bunch of linear constraints on the pi AA. And what I'm optimizing was also linear function. So that this would have been, I don't know, this is summation over A pi AA sigma AA plus. So this was a linear programming problem. Now the quantum version is also a linear programming problem, except that this constraint, okay, is not so simple. So trace pi rho is linear in the matrix entries of pi. Okay, trace of pi sigma is linear in the matrix entries of pi. So remember the unknown is pi only. Okay, but now pi is a matrix. So I want to know pi of a comma a prime. Okay. So the unknown is not just pi of a comma a, but it's pi of a comma a prime. So the only difference is that this linear constraint. Okay, so this gets replaced by remember, so this is the matrix which has entries a comma a prime. So this gets replaced by what is called a positive semi-definite constraint. So this matrix of unknowns has to be a positive semi-definite matrix, and the other inequality says that identity minus the matrix of unknowns also has to be a positive semi-definite matrix. So this is a positive semi-definite constraint. It's no longer a linear constraint, it's a more sophisticated constraint. So the quantum optimization problem has a linear constraint, which is this. Okay, it's linear in the entries of pi. It's the linear in pi of a comma a prime. Okay, the objective function to optimize is also a linear function of pi. Okay, but then there's the other constraint. I mean, normally the constraint which you almost ignore. I mean, that okay, all these like 0 and 1. This linear constraint gets replaced by a semi-definite constraint. So these have been very much studied, okay, in optimization theory, and operations research, and also computer science. So these are called semi-definite programming problems. Okay, so a semi-definite programming problem has some linear constraints, but there are also semi-definite constraints. So the definition of d epsilon h, the hypothesis testing relative entropy, is in terms of a semi-definite program. Okay, so semi-definite program are the next best thing that could happen after linear programs. So that's why I'm just taking the trouble of pointing this out. Okay. Is the definition clear? Okay. So let's go ahead. So this is the hypothesis testing relative entropy quantum case. So let us see some properties of this. So one property which you can always see is that this is greater than or equal to 0.
Pranab, I have one question. So a general SDP does not need the upper bound, right? It does not need things to add up to identity. And just be greater than or equal to 0, and that would be fine, right?
Yeah, yeah. So the other one also you can write it as some greater than or equal to 0 by putting in some additional number.
Additional. Okay, okay. And then you can say that the sum of these two is an equality. And
yeah, you can say that the sum of these two is an equality. So that's a linear constraint. Yeah.
Right, right.
Yeah. I mean, okay. I mean, usually SDPs have this the traditional way that was done in the what is the operations research and optimization literature, and then later on adopted by the theoretical computer science literature, is the constraints are linear, the objective function is linear, and there is just one semi-definite constraint which says that the unknown variables, okay, can be rearranged into a positive semi-definite matrix. Okay, but there's a new way which is actually better for our quantum information theory, which is there in Watrous' notes, where where all the constraints are semi-definite constraints.
Yeah, he calls his version of the standard form of
yeah. So there's a Watrous form, but that's more convenient, at least for many information theoretic applications. Okay, so the objective function is still linear, which you want to optimize, but your constraints are entirely positive semi-definite constraint. But I mean, it's easy to show that they're equivalent. So yeah. But anyway, I mean, we will not get so much into the semi-definite programming aspect. So there are a lot of nice lecture notes also these days which look at semi-definite programming and quantum algorithms or quantum information theory. A lot of nice stuff that has been done. But yeah, I just mentioned semi-definite programming because it's something important. You should know that it exists. And our d epsilon h is a semi-definite program. So d epsilon h is greater than or equal to 0 for all epsilon rho sigma. So this you can easily see. So remember, what am I optimizing over out here? My unknowns are this pi, okay? And whatever it is, pi is less than or equal to identity. So this means that trace of pi sigma is less than trace of sigma. I mean, this requires a little bit of proof, but yeah, it is what while pointing it out. But yeah, for now, believe that okay, pi is less than or equal to identity. So trace of pi sigma is less than or equal to trace of sigma. Okay. And trace of sigma is 1, right? And it's a density matrix.
It requires quite a bit of proof. You want to say that trace of this equal to trace of pi sigma pi, and then you will sort of
yeah, yeah. So I'm going to write it down. It's worth writing down. Yeah. So this, so whatever it is, I mean, the minimum value of this quantity is something which is less than or equal to 1. So when I take the negative log of this, that will be positive. That's all I wanted to say. So it's very clear. So this is very nice. I mean, we have noted this in the classical thing also. Like d epsilon max, okay, can sometimes be negative. Okay, but even d epsilon 0 can sometimes be negative, but d epsilon h is never negative. So that's one very nice feature of the smooth hypothesis testing. So okay. So what do I want to prove? I want to prove. So little claim. So A less than B. So AB are matrices. And C is positive semi-definite. So here A and B are Hermitian. I'm not even saying the positive semi-definite. And C is positive semi-definite. Of course, no. Just another word for that. Then AC is less than trace. Okay. So before you go to matrices, let's look at the scalar analogs of it. Scalar analogs means when these ABC are real numbers. Okay, they're Hermitian. So Hermitian are like real numbers. So these ABC are real numbers. Or in other words, the matrices are 1 by 1 matrices. So 1
can
by
I
1
take a guess? I mean, just a small inter. Can I take a guess as to the proof? And then
wait. So
okay,
I'm
okay.
talking of the like the trivial version of this. So the trivial version is my matrices. So I mean, I'm all talking of square matrices of the same dimension, of course. Okay, and they're Hermitian. So ABC are Hermitian. So Hermitian are the matrix analogs of real numbers. So this in real numbers will just be saying AC is less than or equal to BC. Right. So if A and C are 1 by 1 matrices, so Hermitian just means the real numbers. Okay, and I mean trace of 1 by 1 matrix is just the number itself. So this is just saying that AC is less than or equal to BC. So what have I written out here? If real number A is less than real number B and real number C is greater than 0, then AC is less than BC. It's absolutely simple trivial statement. Okay, for the 1 by 1 thing. But now when I go to n by n, I have to prove this. Is this clear, Hari?
Yeah.
Yeah, Shannon, now you can take it. Yes.
Yeah, so basically I'll first construct a map which is just conjugation with square root C on both sides. Okay. So and since that map is a positive map, so that will sort of respect the operator inequality. So what we get is A less than or equal to B, and by positivity of C and hence square root positivity of square root C, what we get is square root C A square root C dagger, which is the same as square root C is less than or equal to square root B square root C B square root C. So and that is there. So now trace is again a quantum operation. So that will also respect the operator inequality. So we can say trace of square root C, A square root C is less than equal to trace of square root C, B square root C, and then cyclicity of trace, and that's it.
Yeah, so his proof is correct, except that you are assuming that quantum operations respect positivity, in the sense that they send positive semi-definite matrices to positive semi-definite matrices. So that's true, but that's something which we haven't proved.
Oh, okay.
And proving that actually means proving things like this. Okay, so in
Okay.
that sense, what you have said is cyclic. Okay.
Oh,
The more fundamental is to prove things like this. So let's prove it.
okay.
But yeah, the rest of it is correct. So, I mean, what I want to show is, so showing this. So this is equivalent to showing by linearity of trace, the trace of so this is just equivalent to showing it. Now A and B are Hermitian, A less than equal to B means that B minus A is positive similar.
Product trace AC less than equal to trace BC, not trace AB less than equal to trace BC. The first statement.
Yeah, you're right. Yeah. Yeah, that's what I want to prove. Yeah. Okay. So I know B minus A is positive semi-definite, right? That was the definition of A less than equal to B. So this is positive semi-definite. And then C anyway was positive semi-definite. Yes, I'm not writing semicolon. So this boils down to saying that if I have two positive semi-definite matrices, M and N, I'm claiming that trace Mn is greater than or equal to 0. Now, why is this not an obvious statement? In fact, why is this a rather non-trivial statement? Is because if M is Hermitian and N is Hermitian, in general, Mn is not Hermitian. In fact, Mn is Hermitian if and only if Mn equal to Nm. In other words, if Mn and commute. Okay, but there's no reason B minus A will commute with C out. Okay, so you cannot claim that, okay, fine, B minus A is positive semi-definite, C is positive semi-definite, but you cannot claim that the product is positive semi-definite. Okay. So, I mean, if the product was positive semi-definite, then great. I mean, all the eigenvalues are non-negative, so trace is the sum of eigenvalues, so it's greater than equal to 0. Will be done. But the problem is this matrix B minus A times C is not even a Hermitian matrix. Okay. So in general, its eigenvalues are complex numbers. So it's not at all clear that the trace will be a real number. Okay. So now I hope you appreciate how non-trivial that statement is. So let me write down the warning. In general, B minus A does not commute with C. So in general is not even Hermitian. But nevertheless, its trace will turn out to be real and positive. So let's prove this. So this is what Shannon was saying. I use some tricks. So this is same as trace of square root C. Square root C. So what is square root C? Remember, I mean, we have defined these things before. Like we defined even log of positive semi-definite matrices. So C is a positive semi-definite matrix. Okay. So go to its eigenbasis. Okay. You have eigenvalues and take the square roots of those eigenvalues. So that is also a positive semi-definite matrix. So this is the square root C is the unique positive semi-definite square root of C. Okay. And indeed, I mean, square root C times square root C will be C, as you can see, right? I mean, just work in the eigenbasis and you're done. So on the left hand side, C, I could have written as square root C times square root C, the matrix square root C times the matrix square root C. Then I applied cyclicity of trace and move one square root C to the left. Okay. So is this clear? The first step? Ready?
Yeah.
Yeah. So now this thing is positive semi-definite. This matrix square root C, B minus C, square root C. So that is easy to see because, I mean, to check whether it's positive semi-definite, let's say I take any vector v. So for all vectors v, so I'm going to take the bilinear form. So this is nothing but where W is defined to be square root C, the operator square root C applied on the vector V. But this thing is always greater than or equal to 0, right? Because B minus is positive semi-definite. So this is the proof that this matrix is positive semi-definite. So this is where the amazing thing happened. Left hand side, the matrix is not even Hermitian. Right hand side, the matrix has become positive semi-definite. So they are different matrices, okay, but their trace is the same. So this is the power of cyclicity of trace. And now that's it. This is greater than or equal to 0. Any questions about this proof? Yeah. So basically that's what I used. Okay. Yeah. So I mean, if pi is less than identity, the trace of pi sigma is less than trace of sigma. So this implies that so yeah, all this was done to show that the smooth hypothesis testing relative entropy is always non-negative. And I mean, the proof was finally not very difficult. I mean, we saw something nice on the way, but yeah, I mean, I mean, you can appreciate that it was much easier than proving that the Shannon relative entropy is non-negative. So, any questions so far? Okay, so let's go to the next important property of smooth hypothesis testing Hermitian information. So this is, as always, what our favorite property, data processing. Okay, fine. So the data processing inequality, so we know the form of that, so that will be and now, I mean, using data processing is hard to prove for a change. I'm going to prove this now. This is very easy to prove for d epsilon h. It is hard to prove for b, but it's easy to prove for d epsilon h. Okay. So what was the left hand side? Left hand side was, so let me ignore the negative log. I mean, yeah, so the negative log is just reversing the direction of the inequalities. So the left hand side was the minimum. So now I'm in the system AB. So I'm looking at matrices or hypothesis tests on the system AB. So 0 less than pi less than identity. This is the 0 on the system.
So Pranav, I sort of suddenly have a question. So this pi in the definition of DH, that can be any measurement element. It may not be a projector, right?
Yeah. So that's what I wrote here. This is
Okay.
any pure memory.
Okay. No, I always think of pi and see think of projector. So just wanted to
Yeah, okay, maybe the notation. But yeah, so I mean, if you remember the classical theory, there was a
yeah, exactly. There was a fuzzy if, and that's precisely what we want here. We don't want ones on the good subset. We want some probability distribution on the good subset.
correct. Yeah. So the projection version would be choosing a subset of the sample space. Okay. So I mean, there are sample points which I always accept, and there are sample points which I always
reject. Right.
You can do slightly better than by making things fuzzy, like fuzzy set theory. Each for each sample point, you have a notion of acceptance probability. That's why I keep harping on the term private credit card. This is sigma. So this is the thing. Now, so for the left hand side, I'm solving this optimization problem. So I'm hunting for a matrix pi AB. So that's the unknown matrix which satisfies these constraints. And I want to minimize this objective function, which is trace of pi sigma. Now, if I reduce, I mean, so basically, I mean, these constraints define what are the feasible pi. I mean, the set of matrices pi AB which satisfy these constraints are called the feasible pi. And within the feasible pi, I want to find the minimizing pi for this objective function. Now, of course, if I reduce my feasible set, okay, so if I'm not looking at all the possible pi's but only a subset, then the minimization, okay, will not be so good. In other words, this will be less than or equal to the minimum that I would get by restricting my feasible set. So this is my restricted feasible set. So I'm only optimizing over pi A, satisfying and say, I mean, come on, I need a pi on AB, not pi A. So here is what I'll do: pi A and say, and here the objective function also I have pi A. Right? Okay, so what I'm saying is that up here, I was optimizing over all pi AB satisfying these constraints. But now I'm optimizing over a smaller set. I'm reducing my feasible set. So I'm optimizing over pi ABs that are of the form pi A tensor identity. That's basically what I'm doing. They have the form pi A tensor identity. Pi A satisfies these operator inequalities. So let us see on the side. So 0A less than pi A less than identity A. So this implies that 0AB is less than pi A tensor identity B. Okay. So easy to see because 0AB, you can see it's actually a tensor product of 0A times 0B, and this is also a tensor product of identity on A times identity on B. And all that I have to prove is, so a little claim, but now these claims should be easy for us to follow, that if M is, so M on system A is less than N on system A, and let us say T on system C is greater than or equal to 0, I mean, is a positive matrix. So So this implies M tensor T. This one A, this one C is less than M tensor T. So again, this is easy to see. I mean, to show that M tensor T is less than N tensor T. So this is equivalent to saying that N minus M tensor T is greater than is positive semi-definite, is greater than the 0 AC. Okay, but but what am I saying here? I'm saying that the tensor product of two positive semi-definite matrices is positive semi-definite. So that we know. I mean, we in fact know what is this eigenbasis. So the eigenbasis will be the tensor eigenbasis. The eigenvalues will be the pairwise products. Okay, so the eigenvalues are all greater than equal to 0. Okay, so tensor product of two positive definite matrices is positive definite. Okay. And the consequence is like these kinds of things hold, and that's exactly what I've written out. Okay. So what I'm saying is that restricting the feasible set to be of the form pi A tensor identity B is a valid restriction. It's a subset of all the pi A's that I come out here. So the minimization cannot be that good. So that's why I have this less than or equal to sign there. So is this clear? Yeah. Okay. But what is this? This is minimization. Again, now I'll use property of partial trace. Why is it rotated out there? Some button contrast. Identity A. Now I use the property of partial trace. So this is the same as saying trace pi rho A is greater than 1 tensor. So we have seen it already a couple of times that I mean this was also remarked, the fancy of treating it is the adjoint, the partial trace is the adjoint operation of tensoring with the identity matrix under the inner product of matrices. Okay. So I mean, if you have expressions like this, like if you have expressions like the trace of something tensor identity multiplied by some joint matrix, then what I can do is that I can trace out the system B on which I have done the identity. So I can trace out the system B out here, that will give me a rho A, and here I mean I have this matrix pi will come out. And similarly, this is the same as trace of pi A sigma A. It's exactly the same. But by definition, this is D of rho A. Well, whatever. Well, I mean, I did it by removing the negative log. So let me write the proper thing. So basically, the optimal value of the semi-definite program for the left-hand side was this one. It was this one, and that is less than the optimal value of the semi-definite program for the right-hand side. So now when you take negative log, the inequality reverses. So this is saying that D the proof is done. So is this clear? So this is the power of writing this entropic quantity as an optimization problem. So the data processing just boils down to doing an optimization over a smaller feasible region. So is it clear to everybody?
Yeah.
I'll stop now, and we will continue next time. So next time we'll define the d epsilon max. That's also fairly easy to prove. It is also fairly easy to prove what happened. Yeah, it is fairly easy to prove a data processing inequality for that. So at least the smooth one-shot quantities, we have proved data processing inequalities. Then we'll see, I mean, the exact analog. So we'll apply the smooth hypothesis for channel coding and the smooth max for source coding kind of problem. Analog, we to prove the theorems along the way. And then finally, we'll see the asymptotic partition and deduce the data processing inequality for good old relative entropy.